Welcome. This is Dr. Bullock. This lecture will cover gases, vapors, solvents, and particulate matter. Gases and vapors. A gas is a formless matter that fills its container and exerts equal pressure in all directions. It is a gas at room temperature and remains in that state. A vapor is a liquid at room temperature and evaporates, converting to the gaseous phase, and we call that a vapor. Both gases and vapors follow the gas laws related to temperature, pressure, and volume. The vapor pressure and temperature of a chemical are directly related. An example is methyl ethyl ketone, which has a vapor pressure of 100 millimeters of mercury at 25 degrees centigrade and 40 millimeters of mercury at 60 degrees centigrade. Boiling point and vapor pressure also increase with increasing numbers of carbon atoms in a molecule. Example here, we have three different ketones: acetone, methyl ethyl ketone, and methyl isobutyl ketone, which has a boiling point for acetone of 56 degrees centigrade, MEK 80 degrees centigrade, and MIBK of 128 degrees centigrade. The hazards associated with gases and vapors also vary, from asphyxiants, both simple and chemical, simple being that the chemical displaces oxygen in the lungs, similar to water displacing oxygen in a drowning victim, or chemical asphyxiants such as carbon monoxide, which replaces oxygen being carried by hemoglobin throughout our body. They can also be irritants, simple irritants causing eyes, nose, and throat irritation, or central nervous system depressants. Our lectures coming up will include discussions on organic solvents, cryogenic liquids, flammable and combustible liquids. We'll learn that organic solvents are broken down into a number of different categories or classes, being aliphatic hydrocarbons, aromatic hydrocarbons, chlorinated hydrocarbons, alcohols, ketones, and esters. Hydrocarbons are primarily compounds found in petroleum and natural gas. They are made up of hydrogen and carbon atoms. The number of hydrogen and carbon atoms determines what compounds it is. An example is propane and propene. Aromatic hydrocarbons are hydrocarbons with sigma bonds between the carbon atoms, forming a ring formation. We see this in benzene, toluene, xylene, and ethylbenzene, just to mention a few. We also have halogenated hydrocarbons, which are organic compounds consisting of carbon or carbon-carbon bonded atoms or carbon-hydrogen atoms that include the halogen atom, such as fluorine, chlorine, bromide, and iodine. In the workplace, We have potential solvent exposures from parts washers. These are very common sources of solvent exposure to workers in the workplace. Most maintenance shops will have a small parts washer like the one you see in the photograph in their maintenance shop. Maintenance staff uses these parts washers to clean and degrease parts they're working on. These parts washers come in varying sizes and are used in a wide variety of different solvent compounds. For fire protection, most of these units have auto-closing lids that allow the top to fall closed and smother the fire out. It should be a standard operating procedure to keep the lids of these units closed when not in use to prevent solvent vapors from escaping into the workplace. However, in most shops you will see them left open. This is just a poor practice and creates potential solvent exposures for all the workers in the shop. There are also larger units that can sometimes be seen in special industrial processes, and these are used to clean very large components. There are some large enough to hoist an entire diesel engine into. For the larger ones, you will also have a crane associated with the parts washer to lift these large parts in and out of the washer. Solvents are everywhere. We use them almost daily in our household cleaners or in our lawn equipment. This list includes some typical industrial uses. Solvents in surface coatings, paints, lacquers account for about 43% of the use in industry. Degreasing of metal in metal parts cleaners, such as the ones that we've just seen, accounts for about 10%. We spoke about household products, that's about 8%, which includes some adhesives, pharmaceuticals, and then lastly, dry cleaning, which accounts for about 7% of solvent use in the United States. Proper storage, use, and handling of flammable and combustible liquids are a key aspect of workplace health and safety. It is important to understand the potential for fire to occur. A key parameter of this is knowing the flash point of a liquid. That is, the lowest temperature at which a solution gives off enough vapor to support a fire. You can find lists and criteria regarding flash point in a number of regulations. NFPA 30, NFPA 325, and OSHA 1910 Subpart 8. Other key physical properties of a liquid are the boiling point, flash point, and vapor pressure. The vapor pressure is the pressure of a vapor over the liquid at equilibrium. All liquids have a tendency to evaporate into a gaseous form, and all gases have a tendency to condense back into its liquid form. Temperature is the sole factor in reaching equilibrium. Liquids with a higher vapor pressure vaporize more readily than a substance with a lower vapor pressure. We call this volatility. So the higher the vapor pressure, the more volatile the chemical. This is important from a human health standpoint because if the chemical is not in the air, a worker cannot breathe it in. You will also see different combustible classes in the different regulations. We will look at those in more detail. However, the key components are a flammable liquid or class 1 flammable has a flash point less than 100 degrees Fahrenheit and a vapor pressure less than 40 psi at 100 degrees Fahrenheit. A combustible has a flash point greater than or equal to 100 degrees Fahrenheit. Here are the different flammable classes as described by the NFPA and DOT codes. A class 1A is got a flash point less than 73 degrees Fahrenheit and a boiling point less than 100 degrees Fahrenheit. This is the most flammable class that we have. A 1B has a flash point less than 73 degrees Fahrenheit, but the boiling point of that liquid is greater than 100 degrees Fahrenheit. The last class flammable liquid is a 1C, which has a flash point greater than 73, but below 100 degrees Fahrenheit. Remember, the 100 degrees Fahrenheit cut point is where we go from a flammable liquid to a combustible liquid. And combustible liquids are also broken down into a number of classes. So a class 3 liquid has a flash point range between 100 and 140 degrees Fahrenheit. A class 2A has a flash point range between 140 and 200 degrees Fahrenheit. The class 3B have flash points greater than or equal to 200 degrees. The flammable or explosive range of chemicals is also very important. We not only use this for flammable liquid storage and fire prevention, we also use this in confined space entry. Chemicals have calculated values at which there has to be enough vapor in the air to support combustion. This is referred to as the lower flammable limit or lower explosive limit. There is also an upper limit where the amount of vapor in the air is too high to support combustion. This is called the upper flammable limit or upper explosive limit. For those of you that work on cars and carburetors, know this as either too lean or too rich. So we have to have enough vapor to create combustion air in the air mixture. If it's below that level, we say it's too lean to burn. If it's above the upper explosive limit, we call that too rich to burn. When we're talking about LEL or UEL, we report that in percent of the vapor of the chemical in the air, and 1% is equal to 10,000 parts per million. Now let's look at gasoline. It has a very wide explosive range, which makes it more dangerous than a lot of different flammable liquids. This chart shows you this wide explosive range, which for gasoline is 1.4% to 7.6. That's 14,000 parts per million to 76,000 parts per million. Now, as industrial hygienists or occupational health professionals, we usually deal with things like benzene at 1 part per million or formaldehyde at 0.75, or maybe xylene and toluene at 100 parts per million. However, when we're talking about flammable ranges, we're talking in the tens of thousands of parts per million. So if we have concentrations of most of these solvents in the flammable range, we're probably well above safe levels from a human health standpoint. But from a fire safety standpoint, the key is preventing combustion or explosion. A lot of facilities will have safety cabinets in place that are designed to protect flammable liquids from exposure to heat and flame impingement. Many of these have the capacity to vent vapors outside the cabinet. However, this is rarely used. They're not really designed to contain fires, but to provide the liquid inside the cabinets protection from high temperatures or flames for up to 3 hours in some cases. The National Fire Protection Agency came up with a classification scheme several years ago to help protect firefighters and emergency responders. They wanted a system that would give the responders a sense of the hazard without having to look at a safety data sheet or without knowing a lot about the chemical itself. This relative risk ranking scheme tells the responder quickly to what degree the material poses a health hazard, the blue section, a fire hazard, the red section, or a reactive hazard, the yellow section. There is also a special warning item, such as water reactivity or shock sensitivity, on the chart in the white section. This NFPA scheme can be used in the workplace to comply with hazard communication standard labeling requirements, as long as you train all of the employees on how to interpret it and where they need to go to get additional information, such as this NFPA diamond may also be seen in some areas of the U.S. on the outside of buildings. This is typically mandated by some local law to let the fire department know what is the most hazardous chemical located inside that building. The Paints and Coatings Association came up with a similar classification scheme to make it simple for workers to understand the relative risk of chemicals. This is referred to as the Hazard Material Identification System, or HMIS. This label can be used with additional information to satisfy OSHA's Hazard Communication Standard requirements for in-plant labeling. However, OSHA requires additional information such as chemical name, manufacturer name, and target organ information. Now that OSHA adopted the globally harmonized standard requirements, we also have to have pictograms on the labels. Now, we've talked a lot about firefighters and emergency responders. There are a number of other useful sources of information on chemicals that provide the flash point, vapor pressure, lower explosive level, and special handling procedures on many chemicals. One of the primary ones is the DOT Emergency Response Guide, or ERG. DOT also has other shipping labeling requirements for transporting hazardous materials in the United States. This placard shown here has the number 1993, which corresponds to information in the ERPG about how to handle spills and fires associated with this chemical. NIOSH also has a pocket guide of chemical hazard information that helps responders and industrial hygienists to determine what level of PPE might be necessary for the responders. Both the ERG and the NIOSH Pocket Guide are available electronically as apps for smartphones. A very handy tool for the health and safety professional. Now let's talk about some specific health effects of different organic solvents. Organic solvents can have both dermal effects and central nervous system interferences. Organic solvents get into the body readily because they are lipophilic, which means they can dissolve in fat tissue and diffuse quickly through our cells. From a dermal standpoint, organic solvents dissolve lipid or fatty tissue when they come in direct skin contact. This can result in dry, cracking skin and/or other dermatitis, reddening of the skin, or rashes. Other effects may include interference with the barrier function of the skin and allow other substance to enter the body. So if the solvent dissolves the fat out of the dermis and we start having cracks in our skin, other chemicals or compounds that may not have been able to penetrate the skin may get in through those cracks. Organic solvents can also affect our nervous system. Concentrations in the lipid bilayer of our skin and our subdermal tissue can interfere with conduction of responses across neurons, which results in apparent depression of the nervous system. These effects are due to the physical properties of the solvents. Some organic solvents pose a great risk to workers. One example being benzene, which is a colorless or light yellow liquid with a sweet odor. It is found in crude oil and other products and is highly flammable. Benzene is also produced when burning organic materials and is found in forest fires, home fireplaces, volcanoes, and cigarette smoke. Short-term or acute exposure to benzene can cause drowsiness, dizziness, rapid or irregular heartbeat, headaches, tremors, confusion, and unconsciousness. Long-term or chronic exposure can cause adverse effects on the blood and harmful effects on our bone marrow. It is a confirmed human carcinogen, and long-term exposure to high levels of benzene can cause leukemia. Some alcohols, like methanol, which is wood alcohol, can cause blindness. It is not actually the methanol that causes the blindness, but one of the metabolites, formaldehyde, that causes the ocular damage. A very similar alcohol, ethanol, which is grain alcohol, does not have this same effect because the metabolite is acetaldehyde and not formaldehyde. You'll learn more about this process in your toxicology course. This is a list of references where you can find toxicological information on many different chemicals and compounds. You can get information from the container labels, from safety data sheets, documentation of the TLVs, the NIOSH criteria documents for the TLVs, toxicological databases, and other textbooks and monographs. Now we're going to shift gears from gases and vapors to particulate matter. There are several different classifications of particulate matter, such as dust, mist, and fumes. The category that the particulate falls into is based on the size or diameter of the particulate. It is important because this determines how far into the lung the particulate can travel and how easily it can be removed. During one of my previous lectures, we discussed the respiratory system. Within that lecture, we discussed several different defense mechanisms that the respiratory system has. Now, we're going to learn more about the physical properties of the particulates themselves. This diagram shows the average human hair being 150 microns in diameter. A lint particle is next at about 25 microns. Heavy dust, such as fertilizer and pollen, are about 10 microns. During pollen season, we can see particulate on our vehicles relatively easy. That is because of the size of the pollen particle itself. Plant spores and mold spores are between 5 and 10 microns. Bacteria and animal dander are about 1 to 5 microns. Tobacco and cooking smoke and metallic fumes are between 0.3 and 1 micron in size. Viruses are very small at 0.001 to 0.01 microns in diameter. Dry sweeping and using a standard vacuum introduces large amounts of particulate matter into the air. This later settles on other surfaces in the workplace or the home. This is a very inefficient way to clean. Wet methods, or using vacuums with high efficiency filters, such as HEPA filters, should always be considered before dry sweeping or using standard vacuums. We will discuss the importance of each of these aspects, the behavior and deposition of particulate matter, in the next several slides. The use of earth minerals is a common source of dust in the workplace and in the ambient air. Forest fires and volcanoes also contribute to the dust load of the ambient air. Chemicals are often found in powder form and is another source of potential dust exposure within the workplace. Here are some additional sources of dust exposure which come from farms and other sources around your home. A fume is technically a molten metal condensate. Basically, it is the result of heating up a solid, creating a vapor. The vapor then cools in the air and condenses into a very small particle, typically less than 1 micron in diameter. Due to the very small size of these particles, they behave more like a gas in the air. They can penetrate into the alveoli region of the lower lung and diffuse across the membrane directly into our bloodstream. Some other items that can be classified as fumes are rosins because they are solid at room temperature. You may also see reference in some safety data sheets to fuming acid, which is technically incorrect, but it is referred to as a fume due to the small size of the particulate matter. It is really a mist because they are very small liquid droplets that vaporize and condense into a very small droplet. Now, here is my soapbox speech. When you hear reporters and others indicating that gasoline truck overturned on the freeway and citizens were evacuated because the gasoline fumes, or someone might state that while they're filling their car they were exposed to gas fumes, well, you tell them they are scientifically incorrect. Gasoline is a liquid at room temperature. It heats up and becomes a vapor. It is never a solid. So what people should be saying is that they were exposed to gasoline vapors. A mist can be created mechanically by atomizing liquids, rotating shafts and pumps and motors. If oil or water gets on them, will be atomized and thrown into the air as a small droplet. There are also other devices that can create fogs or a mist above a process. Cutting fluids, drill presses may also generate mist. Oil mist, in the case of cutting fluids, is typically seen in manufacturing sites doing a lot of fabricating. Smoke is caused by incomplete combustion of materials. For example, tobacco leaves burn in a cigarette, and they do not completely burn up. And what enters the air are dozens of hazardous gases and particulates, which is the visible portion. We refer to that as smoke. It is typically a combination of larger particles that we can see or that reflect light and smaller particles that are not visible. Those are typically less than 0.5 microns in diameter. The settling velocity or falling speed of a particulate is dependent on the mass, size, and shape of the particle. Larger particles will settle out faster, as well as heavy or dense particles. Lighter particles, or those with a fibrous shape, will tend to settle slowly and can be re-entrained in the air by the air currents themselves or movement around them. The behavior of particulates in air is very important. Distance away from the source or the time it takes to travel are dependent on the particle size. Large particles become fewer as the distance from the source increases. Small particles settle very slow, and again, if we have natural air currents, can remain suspended in the air for very long periods of time. Dilution causes rapid decrease in concentration with distance. That is why we use dilution ventilation in a lot of facilities. You'll want to refer to the figure in your textbook, or there are several figures online that list the standard size or size ranges of different types of particulate matter. This can be very helpful when determining what type of respiratory protection a worker may need, what type of local exhaust ventilation may be appropriate for a specific process, as mentioned in my toxicology lecture. The respiratory system has some good defense mechanisms. Here we will look at particulate deposition and the defense action that our body takes to protect itself or to remove the particulate matter from our body. In the previous lecture on the lung, I talked about the branching pattern of the bronchial section. This design causes larger particles to impact on the walls because of inertia. Particles traveling cannot make the bends in this bronchial tree and impact on the sidewalls. When we measure dust or collect dust on workers or in area samples using the NIOSH 500 method, we are collecting the total fraction of dust, both large particles that will be trapped in the upper respiratory system as well as lower respiratory system. The smaller particles that can make it through the defense mechanisms of the nose and the bronchia and make it all the way down to the alveoli are called respirable particles, and these are particles less than 10 microns in diameter. These particles can stay in the lung for a longer period of time and can be absorbed into the tissue, or which can then potentially be digested by specialized white blood cells known as macrophages in the lungs. This figure shows the part of the lung that different sized particles can penetrate to those that are 5 to 100 microns tend to impact due to inertia and are trapped in the nose, nasal terminates, or throat. Particles 1 micron to 10 microns can penetrate down into the tracheal bronchial regions, where they tend to impact, get trapped, and are removed from the body through that mucociliary excretory system that we talked about previously. And those smaller particles that diffuse similar to a gas and can travel to the alveolar region, the region of gas exchange, are 0.01 to 10 microns in diameter. Particles smaller than the 0.01 tend to go out with our exhaled air and are not trapped in the body. Recently, the American Conference of Governmental Industrial Hygienists, or ACGIH, as well as other international health organizations, started categorizing particles into 3 groups: inhalable fraction, thoracic fraction, and respirable fraction, based on the region of the respiratory system that they can penetrate down into with normal respiration. Based on this, we now have size-selective samplers that can be used to collect specific fractions of dust. Inhalable dust samplers are designed to collect only large particles and are sometimes called button samplers due to their look. These samplers have low inlet velocities and include materials that are typically inhaled, swallowed, or blown out of the human body. It is important to note that using this sampler is not comparable to the OSHA total dust permissible exposure limit, because the fraction of dust that's collected with an inhalable sampler is typically has a higher mass fraction or weighs more than the sample dust collected using the NIOSH 500 method that we mentioned earlier. To get respirable dust, we use a cyclone. This is of particular importance when sampling for silica and coal dust, because we're mainly concerned with the ultrafine particles, or those that are smaller than 10 microns in diameter. A filter cassette is placed on top of this cyclone you see in the photo, and air drawn into the cyclone is generated or creates a vortex or a swirling motion inside. The heavier particles fall out into the red cup. The smaller particles pass through and are trapped on the filter. This sampler has been around for a very long time and has been used for personal sampling since about 1968. This photo shows a number of different devices used to sample particulate matter. If you Google dust sampling devices, you can read more about them. There are cascade impactors, button samplers, other types of impactors, and several different types of cyclones, as well as simple cassettes that are used to collect total dust. This is a cutaway of a cyclone sampler showing you the air inlet, which starts that swirling motion that is similar to a tornado, or as I refer to as a vortex, the cyclone opening, and the different stages of a standard cassette showing how you put it down on top of the cyclone sampler when you're taking a sample in the field. To collect asbestos samples or other fibrous minerals such as fiberglass or mineral wool, use a specific filter, and the fibers are counted using a microscopic method. This counting is similar to how we used to count blood cells in a pathology lab. For asbestos, use a mixed cellulose ester membrane because that MCE filter is dissolved with acetone, placed on a microscope slide, and then read by the technician by actually counting the fibers that they see using phase contrast illumination to distinguish fibers from other dust particles. This is a visual or optic analysis and is not based on chemical compound specific requirements. Here are some different types of collection media. They include standard 37mm cassettes shown to the far left, marked A on the photo, a 25mm cassette such as those used for asbestos with a longer cowling, marked B on your photo, and then to the far right you'll see the breakdown of a button sampler used for inhalable dust. All of these have filters in them that are removed in the laboratory after sampling and are weighed on a tare balance. Personal sampling is a key to accurately measuring a worker's potential exposure. Employees are not static and do not stand in one location. As a result, area sampling is not representative of worker exposure, and the results of area sampling should not be compared directly to an OEL. Historically, area sampling was preferred to personal sampling due to pumps being big and bulky. However, today, we have very small pumps that are lightweight. Area sampling is good for determining what a specific process is emitting into the air, or to screen areas to determine if personal sampling is warranted. Dust control can be as simple as wetting the materials. For example, cutting rock or concrete can be done with a wet saw and all but eliminate any potential silica exposure to the worker. We can also use vacuum systems and local exhaust ventilation systems to remove dust at the point of generation. Avoid dry sweeping or using compressed air to blow down equipment or clothing, as this entrains a lot of dust into the air. Fume control is best accomplished with local exhaust ventilation. Some welding operations can be automated with the use of robotic welders. We see this frequently now in auto manufacturing. This totally isolates the operator from the potential exposure. Where that's not feasible, portable fume extraction systems can be used. The picture to the right shows one of these portable fume extractors being used in a welding shop to remove welding fumes at the source of generation. Mist can be controlled at the site of generation as well, and can sometimes be enclosed with different barriers and different filter systems. The main issue is to minimize generation to the extent feasible. Smoke from combustion engines and different manufacturing processes can be controlled with different filters and wet scrubbers. At power generating facilities, you may also see electrostatic precipitators in place. These are very efficient pollution control devices that remove particulate matter from exhaust streams. In review, there are many different effects of particulate matter on the human body. Some of them are simple irritants. Some of them act as systemic poisons. Some of them can cause sensitization and subsequent allergic reactions. Some of them are fibrogenic, meaning they can cause scarring of lung tissue, specifically silica and asbestos, and others are carcinogenic, such as asbestos. This slide summarizes some of the reactions to inorganic dust. Fibers are caused by asbestos. Scarring of the lung tissue and other obstructive lung diseases can be caused by silica and coal. The damage or hazard is size dependent. Are they respirable versus non-respirable? They're also dependent on the concentration and clearance from the lung, the duration of exposure, and individual susceptibility. Metals have effect on many different systems in the body. However, not all of them are adverse. Some of the metals are needed by our body for normal or essential functions. Iron, manganese, magnesium. Exposure to excess amounts may cause toxic effects. Metals that have primary toxic effects are cadmium, lead, mercury, hexavalent chromium. There's a term welders use called metal fume fever, which has symptoms like the flu or a cold. If you talk to older welders, they will tell you that they have experienced this before, and if you drink a glass of milk, the symptoms go away. Heavier exposures can cause the listed items on this slide. Most physicians and researchers think that scarring of the lung, like we see in asbestos disease, is caused not by the fiber itself, but from the interaction of the fiber with our defense mechanism, that specialized white blood cell called the macrophage. When the macrophage engulfs the fiber and tries to digest it, one theory is that the fiber pierces the nucleus of the macrophage, releasing enzymes to the tissue surrounding the macrophage, which causes the scar tissue to develop. Here is a photo of a fiber penetrating lung tissue. Asbestos has been used for hundreds of years and is known for its qualities being thermal resistant and chemical resistant. It was used heavily in building materials from the 40s to the 70s to help prevent deaths due to fires and thermal burns. One example was in 1958, where there was a tragic fire in Chicago at a Catholic school called Our Lady of the Angels. That fire killed 92 children and 3 nuns who were trying to rescue them. Following this fire, regulations were passed regarding schools, or requiring schools, to use asbestos fireproofing and other asbestos products to prevent similar tragedies from occurring. It wasn't until the 70s that we realized exposure to asbestos presented a hazard to children, and the EPA passed the Asbestos Hazard Emergency Response Act. Children were more susceptible to the adverse health effects of asbestos due to the rapid development and cell growth. Also, at this time, we started seeing asbestos disease in the insulators that applied fireproofing in these schools and high-rise buildings to prevent tragedies from fires. This was also about the same time that shipbuilding boom workers from World War II were showing up with signs of disease. This was all due to the long latency period of asbestos. This slide provides some of the adverse health effects related to asbestos exposure. We can get pulmonary fibrosis, primarily in the lower lobes. This is from high exposure over a long period of time. This results in a restrictive type of lung disease. We typically see a latency of 10 to 20 years after exposure before the disease manifests itself. Asbestos has what we call a synergistic effect between asbestos exposure and cigarette smoking. People that smoke and have exposure to asbestos are 50 to 60 times more at risk of developing lung disease and lung cancers. And on very rare occasions, a disease called mesothelioma may occur. This is usually following very heavy exposure, and this disease has a latency period of 30 to 40 years. Silicosis is another lung disease that has been an issue for around 100 years, if not longer, mostly associated with quarry workers. The U.S. Public Health Department began trying to reduce this disease in the 30s. OSHA has an area on their website devoted to silica hazard and controls. There is a link on this page to a video from the 40s or 50s showing how to use wet methods to eliminate the hazard posed by silica dust. While this seems simple enough and has been known as far back as the 30s, we still see dry cutting of concrete, granite countertops, and pavers today. In the coming years, we're going to note that these small independent business people installing pavers and granite countertops, which are very popular now among homeowners and businesses, come down with silicosis. These smaller companies are often not covered by OSHA regulations or don't know any better. Because of this, OSHA has a significant outreach program to try to bring awareness to this small workforce. I encourage you to go out and look at their webpage and look at some of the information that's out there. This concludes this lecture on gases, vapors, and particulate matter.